Okay, so today what we're going over is we're going over states of matter, and then we're talking about phase changes. A lot of this is stuff that you probably know or at least feel somewhat familiar and comfortable with because you know what a solid is and what a liquid is and what a gas is. You've talked about those things before. You have lots of regular real life experience because you have held an ice cube before, or you've drinking a glass of water, or you've had water vapor from the shower condense on the window, or whatever the case may be. These are things that you have experience with. So we're going to start here with kinetic molecular theory. What does it mean? Kinetic molecular theory. What does kinetic mean? Moving. So moving molecules. Kinetic molecular theory has to do with moving molecules. Are the molecules always moving? In every state of matter? Even in a solid? Yes. So that's some misconception that we've run across a couple times. Yes, those molecules are always moving, even in a solid. So in a solid, they're locked into that crystal structure. But even within that crystal structure, they are still moving. They have vibration within there. No, I'm not going to switch to that right now. Go back here then. That we have solids, liquids, and gases. We want to look at each one of these different states. What's going on with the molecules at that different point? So remember kindergartners. How are the molecules moving in these different states, in solid, liquid, and gas? How are they moving relative to each other and compared to the different states? What would kindergartners be doing, and how would they be like kindergartners in each one of these different states? Yep, solid, they're going to move slower. Remember, they're going to be locked into that crystal structure. They're going to be kind of tied into each other as far as where they are relative to each other. They're locked into that particular structure, and they are moving slower. They just have vibration within their position in that structure. What about a liquid? Now, if we move from a solid to a liquid, how are they moving differently? Yeah, so they're still together. They're not like zoom, zoom, zoom crazy all over the place, but they're kind of moving past each other. They are able to flow past each other in the way that they're moving relative to each other. How about are they moving faster or slower? Or the same? How are they moving compared to the solid? They're moving faster. Yep. And then what about the gas? A lot faster. These are our crazy, wild after lunch kindergartners that are zoom, 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 zoom all over the place. So solids, liquids, gases, how are they each moving? Describe that on your sheet before I show you mine, because I want you to think about it and write down what you think before you just copy mine. All right, what about kinetic energy? How much kinetic energy do molecules have in each of these states? Which one of these has the least amount of kinetic energy, solid, liquid, or gas? Solid, and then which one has the most amount of kinetic energy? And a gas. So again, our kindergartners, our gas molecules zoom, zoom, zoom crazy all over the place. Our solid would be those kindergartners when they're really, really tired and they're just kind of sluggish and they're barely moving along. What about volume? Which one of these has definite volume, which means no matter what you pour it in, you're still going to have the same amount there? And which one has an indefinite volume, which means no matter what you pour it in, it's going to take up all the space it has available to it? Yeah, because if I have my pen right here, if I put it in a different container, it's still going to be the same amount of, still going to take up the same amount of space as the pen took up before. What about a liquid? If I have so much volume in a beaker and then I pour it into a graduated cylinder, is it still the same amount there? Did it take up only whatever amount is there in the graduated cylinder, or did it take up the whole graduated cylinder and all spread out? Yeah, there's only however much there is there. If I pour it into a different container, it's still the same amount that's there. What about a gas? Yeah, a gas is going to take up all the space it has available to it. So picture you have a balloon filled up. That balloon has a certain amount of gas in it. If you now let the air out of that gas, what are those air molecules going to do? Are they going to stay in the same amount of space as the balloon, or are they going to spread out over the whole room? They're going to spread out over the whole room, right? They're not just going to stay like in their little balloon space. They're going to take up, now they have the whole room available, so they're going to spread like kindergartners. If you take a bunch of kindergartners and put them in a bigger space, if you take kindergartners from the classroom to the gym, they're not just going to stay like in their little tiny same classroom sized space. No, they're going to spread out. They're going to run throughout the whole gym. What about shape? Which one of these has a definite shape, meaning the shape is the shape it is. It's not going to change no matter the container. And which ones of these take up the shape of their container? Yep, so again, my pen is pen-shaped no matter what container it's in. What about a liquid? Yep, it's going to take up whatever shape of the container. If I pour it from the beaker to the graduated cylinder, it's going to take the shape of the graduated cylinder. And then what about a gas? Yeah, gas is going to take up whichever space, sorry, now we're on shape. Gas is going to take the shape of its container. So if you blow up a balloon, it's going to take the shape of the balloon. If you blow up a heart-shaped balloon, then it's going to take up the space of the heart-shaped balloon. All right, Jaden, give me an example of a solid. An ice cube. Yep, it's solid water. Kylie, give me another example of a solid.
A table.
Sure. Yep, absolutely. Emma, give me an example of a liquid.
Apple juice.
Yep. Apple juice. That works. Leisha, give me another example of a liquid.
Water.
Water. For sure, absolutely. What about examples of a gas? What's that?
Helium.
Helium is a gas. At room temperature, it's a gas. Yep. What else? What's another example of a gas?
Oxygen.
Oxygen is another example of a gas at room temperature. Each one of these substances that we said those are gas, solid, or liquid at room temperature. If we change their temperature, would they change their state? Yeah, so if we took that ice cube and we changed the temperature of it, would it change its state? Would it no longer be a solid? Yeah, we could melt it and then it would be a liquid. Or we could heat it up even more. It could evaporate and then we'd have, or boil, and then we'd have a gas. Okay. Those are my examples, but they don't have to be your examples. All right, so let's take a look at the bottom part. Have you seen a chart like that before?
Yeah.
Yes, some yes and some no. Did you see it when you just did your choice notes?
Yeah.
Did you see before that?
Kind of. Yeah.
Kind of, sort of. So what we have down here is we've got solid, liquid, gas, our three states of matter. And then we're looking at, okay, are we looking at left to right? So a solid turns into a liquid, liquid turns into a gas. Or we could also look at right to left. So a gas turns into a liquid turns into a solid. You have experience with all of these phase changes. You've experienced with all of these. You have melted an ice cube in your hand before. You have boiled water when you make mac and cheese. You have condensed water from gas water that's stuck in the air. Then it gets cold on your window, you know, when you have water in the air in the house, and then it hits against a cold window and it turns back into a liquid. You've frozen water or other things. I mean, we use water because it's something we're super, super familiar with, but isn't this true for any different substance? Couldn't we take any material and go between a solid and a liquid and a gas? All right, so let's go on this. We're gonna go from left to right. So what we're doing here is we're naming the phase changes. So when we take a solid and we turn it into a liquid, what's that called?
Melting.
Called melting. Yep, so right there, when we go from a solid to a liquid, it's called melting. It requires heat to do that. So if you are holding an ice cube in your hand, so picture you're holding an ice cube in your hand right now. What's it gonna do as it's in your hand?
Start melting.
It's gonna melt. It's gonna turn from a solid to a liquid. Does it require heat to do that? Yeah, for sure. So where is that heat coming from when you're melting that ice cube in your hand? It's coming from your hand, from your body. Some of it from the air, but a large chunk of it from your hand. So heat is going from your hand into the ice cube, and it's doing that phase change. It's doing the melting. That's why the ice cube feels cold in your hand, is because it's taking heat energy away from your hand. So it's requiring heat to do that. The heat it's taking, the heat that it's getting is coming from your hand if you're melting that ice cube in your hand. If you put the ice cube on the counter right there, and what's it going to do if you just leave the ice cube out? It's going to melt. So where's the heat coming from in this case? Yeah, just the environment around it. If you're holding it in your hand, you happen to be the environment. But if it's just sitting on the counter, it's the environment around it, the air around it. There's absolutely heat energy in the air around us, for sure. Okay, so melting right there. What if you go from a liquid to a gas?
Evaporation.
Evaporation is one term. There are two other terms that I want you to be familiar with. So evaporation, what else? What's another word from when you go from a liquid to a gas? What are you trying to do to your water when you're making mac and cheese?
Oh, boy.
Yeah, so boiling is another term here. We're going to talk about how these are different. What about the term vaporization? Have you heard that term? What word does it have in it? Vapor, and vapor is one word that we use for gas water. So these three terms right here I have on the board behind you, vaporization, boiling, and evaporation. All three of them refer to the phase change of a liquid to a gas. All three of them refer to liquid, changing a liquid into a gas. That's a phase change. You're changing it from one state of matter to another. However, so vaporization is a more general term for just a liquid to a gas. When we're looking at boiling versus evaporation, no. So boiling, don't write this down, get what I have on the board. I want to talk about it first because I wrote this as I was writing, and then I didn't want to write it again second and third hour, so I left it. So boiling, when you boil water because you're making mac and cheese, what's the temperature of that water?
Boiling.
It's at boiling point. Would you remember what that is in Celsius?
100 degrees.
100 degrees Celsius. So if you're boiling water, that water, if you stick a thermometer in that water, it's going to be at boiling point. It's going to be at 100 degrees Celsius. But do you remember what temperature means? Remember a definition for temperature? Or do you remember our example for temperature when we were walking around the room? You remember doing that? Okay, so temperature is the average kinetic energy. So when we are walking around the room here, our temperature, the example of our analogy with a temperature, is what is our average speed. So if we are on average, everybody's walking about 1 mile per hour, that's our temperature, and that's our average speed, or our average kinetic energy is temperature. If all of us are moving at, if generally on average, all of us are moving at boiling point, whatever that is, 100 degrees Celsius for water, then we would all be at boiling point. That refers to our temperature. So that would be boiling. All of us on average have enough energy to turn from a liquid to a gas. However, if we are moving at 1 mile an hour on average, does that necessarily mean that every single individual person is moving exactly 1 mile an hour? Might some people be moving a little bit faster and some people moving a little bit slower?
Yep.
Okay, who's the fast person in here?
Emma.
Emma's fast. Or at least she keeps moving. At the very least you just move, which is more than the rest of us could say. Okay, so if on average we are moving 1 mile per hour, but Emma's moving a little bit faster, does she have more or less kinetic energy than all of us as a whole?
More.
Yeah, so she as an individual is going to have more kinetic energy. So if we have a whole beaker full of water, or let's say I forgot to put my tray away from lunch yesterday, so let's say there's a little bit of water on my tray. On average, the temperature of that water is something going to be probably like 22 degrees Celsius. But each one individual molecule that's in there, might some of those be moving slower and some of them moving faster? Yeah. So might one individual molecule happen to get enough energy from the room to be able to do that phase change to turn from a liquid to a gas? That's evaporation. So that's when most of it is not at boiling point. It's at room temperature or whatever. It's not at boiling point. But some individual molecules, because this is an average, The temperature is an average, so some of them are going to be moving slower, some are going to be moving faster. So some of them are going to happen to get enough energy to escape their state of matter. They're going to turn from a liquid into a gas. That's the difference between evaporation and boiling. So in this one right here, why don't we put vaporization? Did you already write something?
Yeah.
Did you already write vaporization?
Yeah.
Awesome, good. So I just forgot what I was doing. And then I got distracted because that happens. All right, let's go the other direction. What about when you go from a gas, turn a gas into a liquid? What's that called? Condensation. Do you have experience with condensation?
Yes.
Yeah, give me an example.
I get out of the shower and then fall down the mirror.
Yeah, so why does that happen?
Because of the hot water in the shower.
Okay, so when you were taking the shower, there's some of that water vaporized, right? It turned into a gas, so now you have a lot of gas water in the air. So that gas water that's in the air, some of that is going to have, well, it's gas water in the air. When it hits the cold window, think about the ice cube in your hand. The ice cube in your hand, heat was moving from your hand into the ice cube, right? So when that gas vapor, the water vapor, that water as a gas, when it hits the cold window, some of that energy is going to be moving from the water vapor to the cold window because heat moves from hot to cold. As it does that, look at these arrows along the top and the bottom. As it does that, it's taking energy away from that water gas into the environment. In this particular example, that's the cold window. So it's taking energy away. It's going to condense. It's going to turn it from a gas back into a liquid. And that's why then you have the liquid on your window. Same thing's going to happen if you have a cold drink on a hot day. Water vapor from the air around you is going to hit that cold glass. Heat energy is going to be taken away from the water vapor, and it's going to turn from a gas to a liquid. It's going to condense. So it's called condensation. So anytime we're moving from right to left on here, heat is being released or being taken away. Every time we go from left to right, it's requiring heat. So when you melt the ice cube in your hand, it's requiring heat energy to go into that process. So heat energy is going from your hand into the ice cube to melt it. If we're condensing water, we're going to go from a gas to a liquid. Heat is going to be taken away from that and going toward, in this case, going toward the cold window. All right, what do we call it when you go from a liquid to a solid? Freezing. Yep, so right here, liquid to a solid is freezing. Do you have experience with freezing things?
Yes.
Yes. How cold is it outside right now?
Like
Below freezing, right? So if you leave your your water bottle outside or or your bird bath, that's going to turn from a liquid to a solid. What about these ones? Either from a solid to a gas or a gas to a solid.
sublimation.
Yeah, which one is that?
Gas to solid.
Nope.
Solid to
Yep. Okay, so from a solid to a gas, that's called sublimation.
How do you spell that?
Like it sounds, S-U-B-L-I-M-A-T-I-O-N.
Yeah.
Sublimation. Sublimation. Okay, so sublimation, we see some examples of that. Later, at another point, we're going to talk about something called triple point. We're going to talk about how pressure is involved here and what if we change the pressure. Because right now, all around you, what's around you right now?
Molecules.
Yeah, air molecules, right? Are they zooming around like kindergartners?
Yes.
So are they bouncing into each other? Are they bouncing into the walls? Are they bouncing into you? Every time they bounce into you, how does that feel? If you could feel it, it would be like kindergartners bouncing into you. So they exert a pressure on you. That's called atmospheric pressure. It's how much normal pressure there is of the air around you pushing down on you and bumping into you. That's not something that you feel generally because that's what your body is built for. What if you went down to the deep sea? Would you be able to feel that different amount of pressure? Yeah, what would happen to your body?
Wouldn't it like
Yeah, you'd get crushed because there's more pressure down there. There's more molecules that are bumping into you and pushing on your body. Your body's not built for that. It's built for atmospheric pressure around here. So it'd be pushing down on you. You'd be able to feel that. Your body would be crushed. Opposite happens. What if you go to space? Why do you need to wear a spacesuit?
So that,
Yeah, right? The opposite. So there's fewer molecules out there, so there's fewer molecules hitting your body, so there's less pushing down on you, so there's less pressure. Your body's not built for that. Your body's built to balance the amount of normal atmospheric pressure around here. Can you feel that, like in your ears, if you go up into the airplane, or if you go down, even in a pool, do you feel that difference in pressure? Yeah, and a pool's not even that deep. Like if you take the lifeguarding class, if you do that certification, like you've got to go get a brick down from 12 feet. Like that's not that deep if you think about it, compared to going down like under the ocean. But that's like, you can feel that. That's a big difference. So when we talk about pressure, one of the things that we can do here, if we can manipulate the pressure, we're going to be able to see some different things happening with phase change. We're not quite there yet, though, in what we want to talk about. Okay, so this one from a solid to a gas, that's called sublimation. What's it called if you go from a gas to a solid? Maybe you've never heard this word before. It starts with a D. Deposition. Have you heard that word before? No? Okay, deposition. Again, spelled like it sounds. D-E-P-O-S-I-T-I-O-N, I think. Deposition. And that's when we're going from a gas to a solid, directly to a solid. In particular conditions that allow for that, depending on what the substance is. Oops, let's go back to mine where it's all filled in. Everything look good? Okay, let's turn the page then. Let's fill in these boxes with the phase changes first before we talk about, first let's look at the axes here, so at least we know what it is that we're looking at. The y-axis right here is temperature. The y-axis is temperature, so as you go up the y-axis, you're increasing in temperature. If you look at the x-axis, it's heat energy, so as you go from left to right, you're increasing heat energy. Sometimes you'll see a graph that looks just like this, but instead of heat energy, it says time. It's the same thing, but why might it say time instead of heat energy? What if I've got my beaker of water sitting right here? As it's heating up, it's gaining heat energy, right? As it's sitting on my hot plate, it's gaining heat energy. Isn't that also isn't it gaining heat energy at a constant rate over the time? Yeah, so that's why it sometimes says time, is because, okay, picture we've got it on a hot plate right here. As the time's increasing, it's gaining heat energy. So if you see time down in the bottom there, like this, if this says time, instead you might want to put that on your sheet, just because it'll help you remember it, so that if you see time, you don't go like, whoa, what is this? But it'll be the same shape. It's just because as time goes on, as we're increasing time, we are increasing the amount of heat energy, and also because it's easier to measure time, we don't directly measure heat energy. We can measure time, and we can assume that the heat energy that's being gained is at a constant rate. Okay, so let's fill in these phase changes here. So what's it right here? Okay, let's do right here, states of matter first instead. Down here where it's coldest, if you've got something that is as cold as it can be, what state of matter is it going to be in? A solid. So this bottom darkest area is going to be a solid. What's next after that if your temperature is increased? A liquid. And then what's next after that if your temperature is increased? A gas. Yep. Within the graph itself, then, are phase changes. So what's it called? If we're looking from left to right again, we're going from, if you look at this arrow that's right there, if we're going from a solid to a liquid, what's that called, that process? Melting. Good. What's the same phase change but the opposite direction? So if we're going now from a liquid to a solid, we're going from right to left on the graph. It's called freezing. Okay, how about this one now? If I'm going from right to left, I'm going from a liquid to a solid, or to a gas, I'm sorry. From a liquid to a gas. Vaporization, or if you put boiling there, that'd be fine too, because this is going to happen at boiling point. And then the same phase change, but going the other direction from a gas to a liquid. Condensation, good. Okay, so we've got this all filled in now. So take a look at these axes. What do these things mean? What's going on in our graph? We're going to start down here in the corner where we have the lowest temperature. If we have the lowest temperature of, again, if we work with water, because we're familiar with water, it's going to be as a solid. If we have solid water, we call solid water ice. If we have solid water and it's really, 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 really cold, and we add heat energy to it, we heat it up, what's going to happen to that temperature of the ice? It's going to increase. It's going to, if it's really, really, really cold ice, we add heat energy to it, it's going to become slightly warmer ice. Because ice isn't just one temperature, right? You could have ice at -1 degree Celsius, but you could also have ice at -100 degrees Celsius or -150 degrees Celsius. And it's not just ice at one temperature. Well, you can have ice at any point below 100 degrees Celsius. I'm sorry, below 0 degrees Celsius. So if we have really, really cold ice, and we add heat to it, it's going to raise the temperature of the ice. It's going to raise the temperature of the ice, raise the temperature of the ice, raise the temperature of the ice until we get to that melting point. So for water, that would be 0 degrees Celsius. When we get to that melting point, and we're still adding heat energy, because look at this graph. So we're moving generally from left to right as we go across. So as we get to that melting point right there, 0 degrees Celsius for water, as we continue to add heat energy, look at the graph. What does it say is happening to the temperature? It's staying the same. It's plateauing. It's not changing. Does it make, let's take a step back, does it make sense that as you add heat to something, the temperature increases? Yes, that makes sense. Okay. But what about this point right here? That as we add heat energy to it, the temperature is not changing. What's going on there? That phase change itself, changing from a solid to a liquid, that process takes energy. That process requires energy to do that. So think about what we know about the molecules, how they're arranged in a solid. So those solids, they're locked into that crystal structure. They're still individual molecules, but there's something in between those individual molecules that locks them into that crystal structure. It's something called intermolecular forces. What's an interstate? What does inter mean? It means between. So an inter